three beasts in outer space. Black holes. Scientists have found the biggest black hole in our galaxy, the Milky Way.
A supermassive black hole is heading directly for Earth. The James Webb Space Telescope, humanity's most powerful eye on the cosmos, has spotted a supermassive black hole lurking in the depths of space. Unlike the distant giants we have encountered before, this one seems to be on a collision course with Earth. Why is the giant black hole headed for Earth? What does its upcoming arrival mean for us on Earth? Join us as we explore the severe consequences of this supermassive black hole that is headed for Earth. As detected by the JWST, the supermassive red black hole is coming for Earth. A supermassive black hole that is extremely red has been found by scientists using the James Webb Space Telescope, JWST, and is expanding in the dark early cosmos. This giant black hole is incredible. It's like packing 40 million suns together. It even makes a super bright light called a quasar, which used to be the brightest thing around way back when the universe was young, 700 million years after the Big Bang. The expanding universe is responsible for the supermassive black hole's crimson color when observed approximately 700 million years after the Big Bang. Light moving toward us is redshifted as the universe expands in all directions. In this instance, the redshifted light shows a thick layer of gas and dust enveloping the black hole. The mass of the supermassive black hole was also measured by the astronomy team led by Lucas Furtak and Adi Zitrin of the Ben Gurion University of the Negev through the examination of JWST data. It is surprisingly big for the galaxy it lives in, at about 40 million times the mass of the Sun. Furtak described their excitement when the first batch of data arrived for the Uncover program. Sifting through the information, they spotted three tiny objects that were both compact and glowing red. These red dots immediately made them suspect they were dealing with something similar to a quasar. Massive amounts of matter surround supermassive black holes like this one to form quasars. The black hole is gradually fed by this matter, which creates an accretion disk, a disk of gas and dust. This matter is agitated by the black hole's enormous gravitational pull, which raises its temperature and makes it shine. Furthermore, matter that escapes the supermassive black hole is directed toward the universe's huge poles. In these locations, particles accelerate into extremely collimated jets that approach the speed of light. This specific supermassive black hole appears as a little point in data due to the huge amount of radiation it is emitting. Rachel Bezanson, from the University of Pittsburgh and co-lead of the Uncover program, reported that analysis of the object's colors indicated it was not a typical star-forming galaxy. She added that this finding further supported the supermassive black hole hypothesis. Bezanson noted that together with its compact size, it became evident that the object was likely a supermassive black hole, although it was still different from other quasars found at those early times. Even with the JWST's powerful infrared sight, the early quasar would not have been visible without a little assistance from an effect that Albert Einstein predicted in 1915. According to Einstein's general theory of relativity, mass-producing objects distort space and time, which are combined to form a single entity known as space-time. According to this theory, the curvature is what gives the object gravity. The more mass an object has, the greater its space-time curvature. Therefore, this curvature not only instructs planets on how to orbit stars and their home galaxies' centers, but it also modifies the routes taken by light emanating from those stars. Light's path is more bent the closer it gets to the mass item. Thus, a foreground item, also known as a lensing object, can bend several light paths from a single background object, changing the appearance of the background object's location. In this instance, light from background galaxies that are otherwise too far away to detect was amplified by the JWST using a galaxy cluster known as Abell 2744 as a foreground lensing body. This displayed the intensely red quasar that they had focused on, which had initially appeared as three red dots. They had utilized a numerical lensing model they had constructed for the galaxy cluster to establish that the three red dots had to represent multiple images of the same background source. He noted that these images were observed when the universe was only approximately 700 million years old. Jenny Green, a team member and researcher at Princeton University, pointed out that all the light emitted by that galaxy had to be contained within a minuscule area equivalent to the size of a present-day star cluster. She elaborated that the gravitational lensing magnification of the source provided precise constraints on its size. Green emphasized that even if one were to pack all the conceivable stars into such a confined space, the black hole would still constitute at least 1% of the total mass of the system. The finding raises more questions about how supermassive black holes, which can have masses up to billions or even millions of times that of the Sun, were able to expand to such enormous proportions in the early universe. Green noted that several other supermassive black holes in the early universe have been discovered exhibiting similar behavior. She remarked that this discovery offers intriguing insights into the growth of both the black hole and its host galaxy, as well as the complex interplay between them, which remains poorly understood. Over time, a multitude of little red dots have been identified by the JWST. These might also point to supermassive black hole-powered quasars being fed in the early universe, which could signal that the confusing black hole growth puzzle will soon be resolved. Zitrin likened the situation to an astrophysical version of the chicken and egg problem. He expressed that currently there is uncertainty regarding which came first, the galaxy or the black hole, as well as questions about the initial mass of the first black holes and the mechanisms by which they grew. James Webb Space Telescope captures the most distant active supermassive black hole ever observed, to the thrill of scientists. Let's dig in. The most distant active black hole. The farthest off active supermassive black hole discovered to date has been identified by the James Webb Space Telescope, JWST. Only 570 million years after the Big Bang, the galaxy that is home to the ancient black hole, Sears 1019, originated very early in the history of the universe. In addition to being unusually old and far away, the active supermassive black hole at the center of Sears 1019 is also unusually heavy, just 9 million solar masses, or 9 million times heavier than the Sun. The majority of supermassive black holes in the early universe have masses greater than 1 billion solar masses, which makes them more visible and easier to find. One mystery surrounding Sears 1019 is the black hole's comparatively small size. The Space Telescope Science Institute in Baltimore, which oversees JWST scientific activities, released a statement saying that it is still hard to figure out how it developed so soon after the universe started. Although smaller black holes must have formed in the early cosmos, astronomers have long suspected this, but these findings are the first to show them in such detail. Dale Kachevsky of Colby College in Waterville, Maine, who led one of 3 new studies utilizing JWST to explore the distant universe, stated that researchers have long been aware of the existence of lower-mass black holes in the early universe. He mentioned that the Webb Observatory is the first to provide such clear observations of them. Kachevsky added that there is now a belief that lower-mass black holes could be abundant, scattered throughout the cosmos, awaiting discovery. In a region of space between the constellations of Ursa Major and Boötes, the black hole in Sears 1019 was found using data gathered by the James Webb Space Telescope as part of the Cosmic Evolution Early Release Science Sears Survey, a research program designed to test and validate methods to peer far back into the history of the universe. Astronomers are already excited about the data that was gathered during the survey. Stephen Finkelstein, an astronomer at the University of Texas at Austin, who leads the Sears survey and co-authored one of the studies of Sears 1019 that utilized JWST data, emphasized that before this development, investigations concerning objects in the early universe were predominantly theoretical. He highlighted that with Webb, The capability to observe black holes and galaxies at extreme distances has now become a reality, enabling accurate measurements. Finkelstein underscored the tremendous power of this telescope in advancing our understanding of the cosmos. About CEERS 1019, JWST was able to gather an abundance of spectrum data, which are electromagnetic signals that disclose the galaxy's mass, chemical makeup, and other characteristics. The galaxy is actively creating new stars. According to the data, this could be the consequence of a merger with another galaxy, which would fuel activity in the central black hole of CEERS 1019. The scan discovered two more lightweights, supermassive black holes with masses lower than those usually observed in black holes at that distance, in addition to the black hole at the heart of CEERS 1019. These two black holes were created 1.1 billion and 1 billion years after the Big Bang, respectively, and are located at the centers of the galaxies CEERS 2782 and CEERS 746. Each mass is approximately equal to 10 million solar masses. With the help of JWST, CEERS survey data, a total of 11 galaxies have been found. These galaxies are believed to have originated between 470 and 675 million years after the Big Bang. According to academics, the information gathered from studying these galaxies has the potential to completely change our knowledge of how stars and galaxies arise and change throughout cosmic history. Pablo Arrabal Haro of Noir Lab, a lead author of one of the studies utilizing the CEERS survey, expressed his astonishment at the vast quantity of highly detailed spectra of distant galaxies provided by Webb. He described these data as absolutely incredible. Peer into the infant universe. The James Webb Space Telescope has captured the never-before-seen starlight from ancient galaxies, shedding light on a groundbreaking cosmic mystery. The starlights from ancient galaxies. In the early cosmos, stars were no longer able to hide from supermassive black holes by hiding behind light. For the first time, scientists have observed illumination from two ancient galaxies that are home to feeding supermassive black holes, or quasars, thanks to the James Webb Space Telescope, JWST. The results may eventually lead to a deeper understanding of how supermassive black holes and the galaxies they inhabit evolve together, as well as how they rapidly expand to masses comparable to millions or billions of suns. Knud Janker, a team member and researcher at the Max Planck Institute for Astronomy, reflected on the advancements in observational astronomy. He noted that 25 years ago, it was remarkable to observe host galaxies from 3 billion years ago using large ground-based telescopes. Janker highlighted the significance of the Hubble Space Telescope, which enabled the exploration of the peak epoch of black hole growth approximately 10 billion years ago. He emphasized the unprecedented capabilities of the James Webb Space Telescope, now available to observe the galaxies hosting the first supermassive black holes. Two of these active galaxies, which are viewed as they were when the universe, which is 13.8 billion years old, was less than a billion years old, were observed by scientists. The supermassive black holes that power the quasars, known as J2236 plus 0032 and J2255 plus 0251, as well as the mass of the galaxies, were both determined. These two galaxies look to scientists to be 870 and 880 million years after the Big Bang, respectively, because it has taken their light 12.9 and 12.8 billion years to reach us. Some of the universe's most extreme objects are quasars. Quasars are powered by supermassive black holes surrounded by gas and dust, some of which are blasted out at velocities close to light, and some of which are accreted to the black hole. Quasars' light output is so intense that it frequently outshines the combined light of all the stars in the galaxy that hosts them. It is thought that supermassive black holes, albeit not all of them are quasars, are at the center of almost every galaxy. For instance, Sagittarius A*, The supermassive black hole at the heart of the Milky Way consumes so little matter that it is the same as a person eating a grain of rice once per million years. It is not feeding enough to support a quasar as a result. Since the discovery of the first quasar in 1963, researchers have figured out the mechanisms underlying their massive light output. The relationship between the masses of galaxies and their supermassive black holes was found in the 2000s. A galaxy's stellar mass is around 1,000 times larger than the galaxy's central black hole mass. For galaxies with central black holes billions of times the mass of our star, and those with supermassive black holes millions of times the mass of the Sun, there is a link between the masses of supermassive black holes and their host galaxies. The fact that both masses increase through a series of mergers between galaxies, which ultimately result in the black holes at the centers of those galaxies violently colliding with one another and creating an even larger black hole, may be the reason for the relationship between the masses of galaxies and their supermassive black holes. As a result, following multiple mergers, a galaxy's mass will be approximately equal to the average mass of the original galaxy times the number of galaxies it merged with, and the mass of the central black hole will be approximately equal to the mass of the original black hole times the same number, resulting in a roughly linear relationship. Another theory is that the radiation emitted by a supermassive black hole that consumes enough material to produce a quasar controls the amount of material that is available to power the quasar and to form new stars. As a result, star production in that galaxy slows down when the quasar runs out of food and stops expanding. Astronomers have not been able to ascertain whether this association holds for galaxies and their supermassive black holes in the very early cosmos, whatever the reason behind it. This is because quasars' brightness makes it possible to study them from billions of light years distant, but it also makes it difficult to observe lower sunlight from galaxies that contain quasars. However, scientists have had to wait for the JWST, the most potent space telescope yet sent into orbit, to accomplish this for older and more distant galaxies. The near-infrared camera, NIRCam, the primary instrument of the JWST, was used to observe the quasars J 2236 plus 0032 and J 2255 plus 0251 for 2 hours at 2 different wavelengths. To see the light from early stars in such galaxies for the first time, the researchers took this combined spectrum of quasar light and starlight for both galaxies and separated the quasar light. The supermassive black hole/galaxy mass link has been found to exist even in the early cosmos, according to remarkable JWST studies of J 2236 plus 0032 and J 2255 plus 0251 and associated galaxies. Though it won't be enough to explain the origins of this mass relationship or how supermassive black holes expand to such enormous sizes just yet, this data will help guide future research efforts. These results are only a portion of what JWST has observed about far-off quasars. The powerful space telescope is presently monitoring 10 more of these objects, which are driven by supermassive black holes, as well as their galaxies. Furthermore, this particular study of the early cosmos has been allocated an additional 11 hours of observation time. Scientists have also come back to say that black holes may not be as rare or distant as we think. The black holes are everywhere. It is now thought by scientists that the cosmos might be made up entirely of microscopic black holes that are traveling through space at the speed of cosmic bullets. Why do scientists believe this? They are running out of explanations for the composition of the cosmos, and while dark matter is a popular but strange theory, it only explains 80% of the universe. Like dark matter, black holes continue to be a source of great mystery, as well as great fascination for us about the cosmos. We are all aware of how they bend matter and light to fit into their vacuum-like existence, turning everything in their path into spaghetti. Thus, A vast number of microscopic black holes that have existed from the beginning of time make up their new supporting hypothesis. This doesn't necessarily solve all the issues, but for over 8 decades, physicists have been unable to uncover the slightest hint of evidence supporting the existence of dark matter and the fact that it controls the gravitational forces that regulate the remaining 20% of the universe's normal visible matter. In a similar vein, the new hypothesis of miniature black holes aids in avoiding the unknown reality. Consequently, NASA cosmologists admit that they are quickly running out of ideas and that there is an extremely slim chance that these imaginary tiny black holes will hit Earth. Even if they do exist, their minuscule size, they are around the size of a rice grain, capacity for deformation, and extreme heat could still result in catastrophic consequences. You shouldn't worry about one striking you just yet, because scientists researching this idea estimate that they would only fly by Earth around once per 100 million years. Every day we crack one enigma, pick up a new skill, and invent new issues for the next generation to work out. While many mysteries still need to be solved, and nature appears to be afraid that there are things we will never be able to understand, science constantly shows us that there is an infinite amount of information available to us and that it is just growing larger and more varied by the day. Forget everything you thought you knew about black holes. The James Webb Space Telescope might be on the verge of revealing how they got so big. How do black holes grow? Usually the biggest, worst, and most violent holes we can envision are the subject of the most exciting black hole news. We refer to supermassive black holes, or quasars, which have masses billions of times greater than the Sun and consume nearby matter so rapidly. The surplus material is ejected in the form of light patterns that outshine the galaxies in which they reside. On March 7, 2024, researchers published a report that should serve as a reminder that there are other black holes besides the villainous ones to consider. Using the reliable James Webb Space Telescope, this group discovered a population of those bright quasars that aren't very massive. They are not that enormous, but they are still supermassive black holes, so that much is certain. In summary, this discovery is significant because, for a very long time, scientists have been uncertain about how some of those quasars get to the enormous sizes that we see. Although the existence of mind-bending huge quasars is known, it is still unknown how exactly these quasars acquire this rank. It almost seems as though not enough time has passed for them to have attained their full shape, despite the large amount of substance they absorb. Therefore, can these recently found, smaller quasars be indicative of a transitional stage of the giants, thereby completing a long-needed gap in our knowledge? Jorrit Matthij, lead author of the study and an assistant professor at the Institute of Science and Technology Austria, pointed out a concern regarding quasars. He noted that some quasars appear excessively massive, surpassing what would be expected given the age of the universe during their observation. Matthij referred to these as problematic quasars. Massive star demises mark the beginning of these troublesome quasars' lifetimes. An extremely large star's intrinsic nuclear fusion activities, which convert hydrogen to helium, begin to slow down as the star draws closer to the end of its life. Such internal fusion eventually comes to an end. This is a problem for a star who wants to escape the clutches of extinguishing. The external pressure that has been preventing the star from collapsing due to its gravity for millions, if not billions of years, dissipates when fusion occurs. The star eventually falls in on itself. It ceases to exist as an explosive supernova, giving birth to a black hole. Then, if this black hole begins to aggressively consume material in its surroundings, it will eventually grow into a massive, dangerous quasar. This is where the problem is. What takes place in the interim? Matthij elaborated on the issue, stating that if one considers quasars to originate from the explosions of massive stars and their maximum growth rate according to the general laws of physics, some quasars appear to have grown at a rate faster than theoretically possible. He likened this scenario to observing a 5-year-old child who is 2 meters tall, highlighting the inconsistency. This is the significance of the team's recent finding of a medium-sized black hole. Perhaps the missing element of the problematic quasar timeframe is represented by these lesser quasars. Matthey emphasized the significance of black holes and supermassive black holes, considering them possibly the most intriguing entities in the universe. He acknowledged the challenge of explaining their existence, but noted their undeniable presence. Matthey expressed hope that their research efforts would contribute to unveiling one of the greatest mysteries surrounding the universe. The objects, which the team lovingly names baby quasars, were discovered by the JWST as multiple small red dots, according to the researchers, in a dramatic manner. Matthey outlined the distinctions between the problematic quasars and the little red dots, describing the former as blue, exceptionally bright, and possessing masses in the billions of times that of the Sun. In contrast, he characterized the latter as akin to baby quasars, with masses ranging between 10 and 100 million solar masses. He further explained that the red appearance of these baby quasars results from dust obscuring the black holes, which causes a reddening effect on their colors. Crucially, the reddish hue also confirms to the team that these discovered black holes are, in fact, quasars, meaning they are actively eating or will soon be feeding. According to the researchers, the targets they are observing are releasing wide-line profiles along with high spectral emission lines. They claim that as hydrogen atoms are heated, these spectral lines are released, and the width of the lines may be used to track the speed of the gas. The gas velocity increases with the width of the line's base. Matthey indicated that the observed spectra imply the presence of a very compact gas cloud exhibiting high-speed motion, orbiting an immensely massive object such as a supermassive black hole. The team's next logical move is to look into these infant quasars in greater detail to establish a genuine connection with their big brother quasars, which have been posing problems for scientists' calculations of black hole genealogy. Even better, though, the team is generally rather enthusiastic about the data sets that the JWST acquired of the area of space that it studied. The data's primary collaborator, Eiger emission line galaxies and intergalactic gas in the epoch of reionization, wasn't even intended to search for the red spots it discovered. It was merely by chance that Matthey's crew discovered them. Matthey illustrated the scale of their exploration by comparing it to extending one's arm and pointing with their index finger. He noted that the region of the night sky they explored corresponds to approximately a 20th of the surface area of one's fingernail. Matthey emphasized that their current efforts likely represent only a fraction of what lies beyond, suggesting there is much more to uncover. The JWST is a marvelous invention that continues to help us see way beyond anything we could have comprehended. The brilliance of the JWST. Although the James Webb Space Telescope and its enabling technology are nothing short of revolutionary, the Hubble Space Telescope is sometimes referred to as the forerunner of the James Webb Space Telescope because of its larger primary mirror, which measures 6.5 meters, more than 2.5 times the diameter of the Hubble. These powers will completely reshape our conception of the cosmos. The James Webb Space Telescope is a remarkable instrument due to its engineering, not its size alone. Its sensitivity and resolution reach previously unheard-of levels. To optimize infrared reflection, a thin layer of gold has been added to each of the 18 hexagonal parts that make up the structure. It can modify individual mirrors, making in-flight calibrations possible. Ideal imaging performance is guaranteed by this architecture, even after deep space operations and launch-related wear and tear. The telescope is not orbiting the Earth like Hubble is, which is another intriguing observation. Approximately 1.5 million kilometers from Earth, at the second L-range point, or L2, is where the James Webb Space Telescope is planned to be located. At this time, the telescope's orbital motion and the gravitational attraction of the Sun and Earth balance out to allow it to hover in a stable location about these bodies. The telescope can observe the universe unhindered by Earth's atmosphere or thermal emissions thanks to this unique location. By concentrating on infrared observations, the telescope can see farther into the past than it has ever been able to, enabling scientists to examine the genesis and development of these old galaxies and offer new perspectives on the early stages of the cosmos. However, its capabilities in the infrared don't end there. It is also a perfect tool for researching how stars, black holes, and planetary systems, like the ones in our own Milky Way galaxy, emerge. Collecting light from the first galaxies to form after the Big Bang is one of the telescope's key goals. It has been applied recently to delve deeply into the mysteries of gas planets. What are your thoughts on the recent black hole finding made by JWST? Don't forget to share your opinions in the comments. Hit the like, share, and subscribe buttons on the channel to see more videos like this one.